think we can start. Hello, welcome to our CSE PhD seminar. Today's speaker is our colleague, student at our PhD program, Mr. Mohammad, Helal, Uddin. So he started his PhD program in 2021, and he is working with his advisor under supervision, Dr. Sabur Baidia. His research focus on advanced neural network optimization, including Hessian-based pruning for convolutional networks and dynamic token head pruning vision transformers, aiming to make deep learning models more efficient for deployment or resource-constrained systems. Okay, before starting his PhD program, he earns his master's degree in South Korea, where he developed a strong background in machine learning and artificial intelligence. Today's topic, I hope I will read correctly, it is, I just counted the number of words, and there is 12 keywords in one title. And what is very important, one of the keywords is not deep learning, and everything is about deep learning, But the title of today's presentation is CAMP-HiVe, that is shortened notation, Cyclic pair merging based efficient DNA pruning with Hessian-Vector approximation for resource constrained systems. Okay, if you still don't understand, believe me, I don't understand. I hope the speaker will explain.
Yeah, okay.
It's your time.
Thank you so much. Thank you so much for the introduction, Dr. Kandrajit. So, hello everyone, I'm Mohammad. So, good afternoon to you all. So, today I'm going to present in this CSE research seminar. So, let me briefly introduce myself. I'm a PhD candidate, as Dr. Kandrajit said, in computer science and engineering department. I work with Dr. Sabur Baidia, my advisor. So, our lab name is AIMS Lab. It's called Autonomous Intelligent Mobile System Lab. So I usually sit in LADI. And there are some of the research work in here I have published in recent years. And if you want, you can find me in Google Scholar and LinkedIn as well. So today we will discuss about the motivation behind this work. So as you know, the topic name is CAMP-HiVe, cyclic pair merging based on efficient DNA pruning with Hessian-Vector approximation for resource constrained system. So we'll go through the motivation, why efficient the efficiency is crucial for deploying the deep learning networks in edge embedded system. Also, I will try to explain the core idea behind this CAMP-HiVe and some of the mathematical foundation behind this work. I will try to go through the algorithm as well. And we have done some extensive experiments on Cypher 10, Cypher 100, and ImageNet 1K dataset. And we use model ResNet 18, ResNet 56, and the MobileNet B2. So, and also we did evaluation our results on edge devices, Jetson Orin devices. So I will go through that result as well. And lastly, we'll talk about like the future research directions. So this paper has been accepted to the ICMLA this year. So I will present this paper this year. So, yep. And okay, let's talk about little bit the motivation thing. So, as you know, the deep learning network story is very powerful, but in the opposite side, you know, the DNN consists of hundreds of parameters. That actually, this kind of massive parameters restrict in like competition and memory cost and all those things. So also when you move from research to deployment, say like mobile or embedded systems or drones or something like that, these models actually hit really real world limits in energy, latency, and storage. So the goal is pretty clear for us, like reduce the flops and power consumptions without losing the accuracy. So efficiency is, it's just not about the speed. So it's about like enabling AI to run like everywhere, not just expensive GPUs, like your phones, your smartphones and edge devices and all this all. So this motivates actually create our journey toward smarter, lighter models. Well, now let's quantify this growth. So as you know, like the GPT-3 and GPT-4 has over billions of parameters. Like if I specifically say, like GPT-3 has like 175 billions of parameters in the model, and in the GPT, also GPT-4 has around like one terabyte of parameters, or like 100 gigs of parameters. So this is really extensive and large models. So training one of these large transformer can emit like 500 ton of carbon dioxide emissions. That is like 5 cars lifetime carbon emission. So deployment is even like more costly, like billions of inference daily cost like thousands of dollars of GPU's time for each month. So we say like bigger is no longer means better. So we need to have models that is like smarter, leaner, and sustainable, which is the key driving force behind this CAMP-HiVe algorithm. Well, as you can see, like edge devices, like edge AI runs on robots, drones, cameras, and IoT sensors. So these devices are resource conscious sometimes, like device with less than 10 watt of power and restrict like latency budget, like around 30 millisecond or something like that. So if you want to achieve the real time, performance in this kind of devices, then you really need to strict. There is some resource constant in there. So so relying on also the cloud inference adds more delay, like cost and privacy risk as well. So like I can give you one example in drones. Like drones have the batteries that has the limited power. So if you like your goal should be fly for the maximum time, but you need to do the performance as well. So if you want to deploy like a large, I mean the larger models is not feasible to deploy on the drones because it's a resource conscious. It will not run on that smaller devices. So in that terms, you also need to make it smaller. The original models. And also about the power. So if you run this model, the optimized model in the drone, it will like consume more power from the drone. So it will run for like less number of time. So the goal should be run for the maximum amount of time, but limit as much power consumption as possible and get the maximum performance from the AI algorithm. So yeah, so in our lab we also did like a closed loop operation as well. Like you will capture the image only from the drones, then you will send it to the nearest edge, more computing able device. Then the device will do the all the if it's image recognition or object recognition, it will do all those things in that device and it will give the feedback to the drone, and drone will move according to that feedback. So there is some delay. In closed loop there is some delays in there as well. So if we can deploy something like locally in the drone that will get the similar kind of performance, that would be like amazing thing to do. Now, our work is mainly based on pruning. So before going to challenge in current pruning methods, let me explain the pruning a little bit. So what is pruning in deep neural networks? So as we know, like deep learning models, they are connected with different layers. So each layer has a number of nodes. So each node is connected with the layers with a connection. So each connection represent a weight. So this weight actually changes over the time when it get trained, the model. So these weights, sometimes they are redundant, means they carry the same information, maybe multiple weights or maybe thousands of weights may be carrying the same information. This is called the redundant information weights. And some of the weights are their magnitude is really small. They contribute really small to the model. So pruning means, so over the time, so the researcher actually find out these redundant and less important weights, and they remove it from the model. So removing it models means they make these weights to 0, so they will not contribute to the flops. So that's how you can optimize your model performance. So now, so as you can see, I have given a timeline from 2016 to now. So over the time, people have developed like a magnitude-based pruning, random pruning, and second order Hessian-based pruning. So what does that mean? So magnitude-based pruning is kind of like you will rank every weights in your models from top to bottom. So from the bottom line, if you like want 70% weights to keep and 30% weights to deduct, then you will say like, okay, so I have sorted out all my weights, so I will deduct my 30% lesser weights from the bottom. So you will keep the 70%. So that's how actually magnitude-based pruning works. And the random pruning is, it actually don't see anything. You say like I will deduct 30% of the weights from my model. It will randomly see like 30% weights, and it will collect 30% weights from your model randomly, and it will deduct from there. So what is the problem in there? So in random pruning, it will not see like which one contributing to your model, which models contribute to your loss function more and less. It will not see that. So you will lose your information from your model. And the second order Hessian-based approach, Hessian-based approach is very important, one of the prominent in this field. But the problem is, if you want to go through with the full Hessian matrix, it's like infeasible in nowadays. Why? I will show later. So, but in our model, we were able to bypass that. So that was one of our contribution too. Okay. So another issue is, like as I said, so most methods like removes connections causing I mean like the information loss, as I said. So what we want a framework that reuse existing weights and retains the knowledge. So our solution is cyclic pair merging. So that means like merge less significant weights with the significant weights using the curvature guidance, so that we can have a compress while redistributing the knowledge regarding that, like throwing it out. Excuse me. Okay, so our goal is to like develop a Hessian guided cyclic pair merging framework for efficient DNA pruning. So we have contributed in so many like objective levels. Like our first contribution was like CAMP-HiVe algorithm that we developed, like curvature aware cyclic pair merging for balanced compression. Then we contribute on the Hessian-Vector approximation. Instead of full Hessian, we use the Hessian-Vector approximation. One of the main contribution is edge device validation. So if you see like the table, it's a comparative table, novelty timelines that actually highlights the objective level contribution. So like most, we have actually mentioned like there are lots of lackings on the subjective level contribution in other methods. So we mentioned those lackings in our work, especially on the edge device. So other works actually they didn't mention practical works They did develop the algorithms and all those things, but deployment on the edge device was a real challenge. Now let's overview our CAMP-HiVe pipeline. So our pipeline has 4 stages, like compute Hessian-Vector approximation to estimate the curvature sensitivity, then rank and partition weights into significant versus less significant groups. Then the third step is cyclic merge, the low importance weights into high important weight ones guided by the curvature. And then the stage 4 is optional, fine tuning. So we have seen in our work like up to 45% work you don't need 45% of reduction in the model, we don't need the fine tuning. After that the accuracy get degraded. In that period you might need fine tuning for the model. So this is an optional one. Now let's talk a bit about the mathematical formulation, the harder part. So now that we have seen how CAMP-HiVe actually operates conceptually, let's look into like mathematical foundation that governs our pruning work. So this part will explain how we estimate the loss change caused by the pruning. The key to knowing which weights actually matter most. So we begin with a standard supervised learning formulation. Here you can see like the xi are the inputs and y are the labels, and n is the total number of training examples. So the model has the parameter w, and the total loss is mean of all sample losses. So far this is a standard. We are just defining in the landscape where the model actually lives. So now the key question is what happens to the loss when we prune these weights? Now to answer that question, we take a Taylor series expansion of like a loss w plus a del w around the current weights of w, where g means the gradient and h means the Hessian matrix, and del w is the change of weights after pruning. Now the first term you see like a del w over t g. So this measures the linear sensitivity, and the second term measures the curvature. And the third term you see in here is capture the higher order non-linear effects. So for larger scale of the network, like the big networks, so this third order term is actually negligible. So because here the curvature terms, the Hessian terms actually dominates. So we simplify our analysis to the second order approximation, which leads to the Hessian-Vector approximation of CAMP-HiVe work. Okay, now so this curvature term actually tell us how fast the loss increases when the weight is actually changed. So essentially it means like measuring the the importance of the weights. So like I can say a weight sitting like on the steep part of the loss surface, I mean the high curvature. So those are the most critical, because and removing those weights will make your loss function be shaky. And the weights in a flat region that actually contribute the less. So these are the weights that we actually target. That these weights are safe to merge, safe to prune, safe to delete from the model, so you can do whatever you want. So therefore actually by estimating these Hessian del w very efficiently, we can determine which weights to retain, which to prune, which to merge, and which to eliminate. Now given this approximation, pruning becomes an optimization problem. Now here C is the cost function. Typically cost means like the flops, latency, or memory. And C budget represents the allowed computational constraint. So this turns pruning into like a constraint optimization problem. So we minimize the change in loss while ensuring the compressed models remains within the given computational or hardware limit. Now, now come back to the connecting to the CAMP-HiVe. So CAMP-HiVe uses this formulation to estimate how safe each merging operation is. So now, instead of computing the full Hessian, which is huge, we compute the Hessian-Vector products to approximate the curvature efficiency. So I will show how we are calculating the Hessian-Vector. Well, now on the previous slide, as you see, like as you saw, that the second order term in Taylor expansion, I mean the Hessian term, captured the curvature and the importance of the weight. But directly computing, I mean the Hessian in the modern network, as I said, is practically impossible. So what we did, so in our CAMP-HiVe, now you'll see like CAMP-HiVe bypass that full Hessian matrix and produce the Hessian-Vector products, that is HB, and estimated efficiently through the power iteration. Now, the Hessian term, I mean the Hessian H, is like an n into n matrix. So where n is the number of weights. As you said, like these weights can be billions. So for today's deep learning network, as I said, it can be billions and millions and billions. So storing or like multiplying by h, the cost could have been like O(n) square time and memory. So which is, as I said, completely like infeasible to do. So instead of every forming Hessian explicitly, so yeah, CAMP-HiVe actually computes only H and B, which is a Hessian-Vector, the product of Hessian with a vector. So this gives us the curvature information along a single direction without touching the full Hessian matrix. Now in the power iteration, if we repeatedly multiply the Hessian by a vector and normalize it, the vector gradually aligns with the dominant curvature directions. That is basically, I would say, eigenvector of the largest eigenvalue. So the direction tells us like which way the loss surface is. I mean the where is the most important weights and where is the less important weights. I mean the sensitivity. So we approximate HB using gradients. No need for like second order differentiations. So for iteration key, as you see in the equation, here is what's happening. So we take a small step, epsilon b over k, from the current weights, and we compute the gradient, and the difference of these two gradients is scaled by 1 by epsilon. That actually approximate hb over k. Then we normalize the results to keep it in a numerical stable. So each iteration refines the direction until it converges toward the strongest curvature axis. Okay, sorry. Okay, so once we have the new bk for a given layer k, we measure the significance of each weight excuse me, as the magnitude of its corresponding entry in that vector. Now the large sigma j means the loss change sharply in that weight moves, means the significant ones. And the small sigma j, the loss surface, I mean the flat region, is the less significant ones. So these values actually act as a curvature error importance for each layer. So now to separate this significant from the less significant weights, we defined a threshold per layer using a quantile cutoff, where QP is the pth percentile. Like for example, as I said, like you can set it like p equals 0.7 or 0.5, 0.4, whatever you want. So weights with like a v nu k is greater than theta that are preserved, and the others are candidate for the merging. So this balances the compression across layers and prevents like over pruning. Now, sorry. Now, so did I change it? Wait a minute. No, okay, yeah, I got it. Okay, so now let's see like why it's work for us. So like each HB like computes cost roughly the same as like 2 back propagations, back propagation passes. So, but still the complexity is within ON, not on the ON square. So the resulting vector actually captures the dominant curvature direction, giving a low cost approximation of like a true Hessian sensitivity. Now that we know how CAMP-HiVe actually estimate curvature and assign each weight an important score, now the next question is how do we compress the model without throwing the information away? So now, now this slide actually introduces the cyclic pair merging rule. So this is one of the main part of the CAMP-HiVe. So now after applying the layer wise threshold theta we discussed earlier, every weight naturally falls into one of the two groups, right? So S represents the significant weights that actually represents the keeper weights that actually strongly influence the loss, and the L represents the candidate for merging. So at this stage actually the network analyzed everything but not modified yet. So now we simply deleting the less significant one, as the other pruning method like magnitude pruning would do, will cause the immediate information loss. But instead of that, CAMP-HiVe actually recycle those weaker weights and transferring their contribution into the stronger ones. But how do we assign which weak weights actually with the merge with the stronger weights? So that's where the cycling merging rule comes in. Now in CAMP-HiVe we define simple rules of the function in here, where S you can see like where S is the number of significant weights, and I actually iterates over actually iterates over the indices of all the less significant weights L. So this formula means for like each significant weights like W less finds the partner. I mean partner means the partner of significant weights by a process of cycling through the significant set of weights. So even if the L, I mean the significant weights set and the S is the less significant sets are not similar, the pairing wraps around automatically because every week actually finds a home. Now once the pair is identified, CAMP-HiVe actually performs the merging. The knowledge that is stored in the less significant weights is added to the stronger ones. The weaker weights then actually zeroed out, means the pruned, then is create the compressed and knowledge redistributed parameter set. So in analogy, you can think of it like pouring a small drops into like a bigger buckets, but there is no water loss, but the bucket amount is reduced, something like that. So now let's see the algorithm. So we have actually discussed almost everything in this algorithm so far. So let's go through the algorithm once more time. So we first actually estimate each layer computational cost. That actually quantify like how expensive each layer is. So it helps later to balance the pruning strength, because pruning in a heavy layer saves like more flops than pruning in the lightweight one. Then for each iteration, we start with a random vector B. For each mini batch, like compute the gradient, then approximate the Hessian-Vector product, then we normalize the B to prevent the numerical explosion. So after several iterations, so B aligns with the dominant curvature directions, giving layer-wise curvature sensitivity. So for each layer L, so we extract the weights W, sort them according to their curvature sensitivity, and then split them using the importance threshold that we saw in the last slide, epsilon into like W significant and W less. Then we do the pairing rules. So each less significance weight is paired with the significant one using the cyclic indexing. So this guarantees actually a full coverage and a balanced redistribution. Then the weaker weights kind of like donates its learned information to the stronger counterpart. So the weak weights then is zeroed out, effectively pruned. The model weights are updated accordingly. Then we go for the fine tuning steps. That's actually optional. If you want to do, you can. If you don't, then it's fine. Now let's see how we designed our experimental setup. So we have used the data set Cypher 10, Cypher 100, and ImageNet 1K data set. And we use the models ResNet 18, ResNet 56, and MobileNet B2 as well. And training protocol, as usual, 100 epochs, and the Adam optimizer, and base size 128. So in here, we also implemented the early stopping for 100 epochs. So if the curves actually converge earlier, so the model will automatically stop the training. So so evaluation metrics, actually we calculate top 1 and top 5 accuracy, flops, reduction, and latency, as well as power for our edge devices. And in edge hardware, we use NVIDIA Jetson Orin with different configuration like 16 gigs and Nano 4 GB, AGX 32 GB. Now let's see some of So now let's see some of the results in here. So you will see like here some state-of-the-art methods as well. So we present all the results together, and in the figure we visualize actually top 3, including ours, top 3 models, how their delta accuracy is. So you will see like our method almost for ResNet 18 in Cypher 10 dataset. Our method gain delta accuracy. Delta accuracy means that the pruned accuracy minus the baseline accuracy. So our method actually achieved like 0.43% more delta accuracy than the others. I mean, delta accuracy of pruned accuracy and between the pruned and the baseline accuracy. The nearest one is ATO. So they achieved like 0.10% of delta accuracy with the similar kind of flops reduction, which is 80%. And in the ResNet 56, the trend is also same. So we have achieved like delta accuracy 0.27%. And the nearest method that actually achieved 0.24% is also ATO. But you will see like their and ours are kind of almost neck to neck, 0.24%. Their one, our one is 0.27%, but we reduce the flops more. They did 55% flops reduction, but we did a 60% flops reduction in that case as well. So in here, our model is also doing great. And in MobileNet B2, we achieved like 0.93% of delta accuracy. The nearest one, so the nearest one actually achieved 0.33%. So you can see like for all the models in Cypher 10 dataset, our method is actually exceeding all the other state of the art results. Now in Cypher 100, we also see the similar kind of trend. You can see like we achieve like 2.79% of delta accuracy. So ATU version 2 didn't have the delta accuracy, but ATU has the delta accuracy, that is minus 0.07. So our one is like a significant one. Now let's discuss on the ImageNet 1K dataset. So we did our experiment on MobileNet V2, and we also compare our result with some of the state of the art result as well. So here you also see like we have achieved like delta accuracy on 0.55% with flops 30%, flops reduction on 30%. With the similar kind of flops reduction, the nearest one was ATO, was like plus 0.14% of delta accuracy achievement. So in all the models and the different data set, our models are continuously exceeding the other state of the art results as well. Now let's see on the feature map analysis. So this is a mean absolute deviation called MAD. So in our MobileNet B2 in the left, you can see from block 1 to 10, the MAD values are low and stable. So the black one is the baseline. So your target should be aligned with the baseline or below the baseline. That would be better. So you can see from block 1 to 10, the MAD values are low and stable kind of. So in all pruning ratio in our model, like 30, 50, 70, and 80% pruning ratios. So this means in the early feature extraction, like edges, color, or textures, our model is doing good in terms of pruning. So their representation almost remains similar. We can say like around 80 to 90% feature is intact. So around the block 11 to 13, you can see there is a certain jump on upward in the MAD across the pruned models. So this indicate like an abrupt rise in the feature map deviation. Pruning has caused a strong representational shift in these layers. This corresponds to like MobileNet B2 channel expansion zone, like a high curvature region where feature actually become more, I can say, entangled. So pruning temporarily causes the representational drift. But if you notice that after from the block 13, it actually the MAD actually drops again afterwards, showing the CAMP-HiVe actually rebalanced the network throughout the curvature guided merging and fine tuning. So now in summary, like the spike actually highlights where the most sensitive zone is, and the recovery shows that our method actually manages to stabilize these transitions. And in the right side, ResNet 56. So you can see like our all the version of pruning models are almost aligning with the base model. So that means it's doing good. You will see like that there is a spike on pruned 50% at convolution layer con2D 108. So we cannot say like it's because of the pruning, because if it's because of the pruning of 50%, then we would see the similar trend for the 70% and 80% pruning as well. So it might be because of some noise and maybe something else. So I still don't know why this actually spikes happens in here as well. So now these are the edge device experiment on Jetson Orin. So as you know, we deployed the pruned models on Jetson Orin 4GB and Orin AGX 16 gig. These are the very popular embedded AI boards actually. So in the latency results, you will see like on Orin Nano, inference latency dropped around like 24, I can say 23.4%, and or in AGX latency actually decreased like 17.6%. So in the region of power consumption, the average reduction is around 5%, and this actually consistent throughout all the devices. So these are not actually the simulations results. So these are all measured on like wall clock improvements using the NVIDIA Jetson states. So now, so with this result, now we can see like this compression model is load like faster, uses less RAM, and allows like a multi-model co-development on the same device, which is crucial for the multi-sensing edge intelligence. Now, so we can say like CAMP-HiVe is not just a theory. So it's an like edge ready optimization. I mean the optimization validated in this field for deployment in the edge devices. Okay, so now we did an ablation study and comparison within our models. So the ablation study happens on Hessian plus a random pairing and merging pruning. So random pairing means like as we described, like the significant weights will pair with the, I mean the less significant weight will pair with the significant weights. So we are using the cyclic merge, but here we are using the random pairing. I mean any significant weights can pair with any less significant weights can pair with any significant weights. So that's called the random pairing, and also a Hessian plus a magnitude pruning and a magnitude pruning alone, and CAMP-HiVe hours. So you can see like our one is like the CAMP-HiVe is doing better in here as well in our ablation study. So it's consistent accuracy retention across all the pruning ratios and confirms the value of curvature over weight distribution as well. Now let's compare the state of the art results with our one. So you can see like there are lots of state of the art results in here. All the methods are in here. Our one for the MobileNet B2 is also in the top in the right corner, and for the ResNet 56 is also in the right in the top corner, which implies that our model is doing much better than the other one. Okay, for now the future work directions. So as you know, like we are doing the cyclic pairing work. So this is not the optimal pairing solution we have found. So so we are trying to find the optimal solution for this pairing optimization problem. So one of the algorithm we are right now looking into like a bipartite matching for optimal pairing. And another one is we are looking for graph neural networks for adaptive pairing optimization. So this is the two algorithm we are looking for our journal extensions of this work. And another algorithm we are trying to develop like caching driven efficient Hessian computation. So this will be, as you see, like I said in my algorithm slide, algorithm 1. So this will be our algorithm 2. So that will use the caching for the Hessian matrix to to keep it in the cache and to reuse it for further. That will I mean give the faster training time as well. Okay, so we actually extended this work beyond the CNNs. We have developed a heartbeat. It's a Hessian guided efficiency dynamic attention head and token pruning. So we have developed a transformer pruning algorithm as well. So this, as I said, this extension of this CAMP-HiVe is for the Vision transformers. And we are dynamically pruning tokens head, I mean the attention heads and tokens using the gradient based, gradient based Hessian sensitivity. So there we also achieved some impressive results. That's the state of the art, and we submitted this work to ICLR 2026. So I hope it will get accepted. So Yes, and in the conclusion, we can say like what we did for this work, curvature error efficiency for our CAMP-HiVe, I mean using our CAMP-HiVe algorithm, and information preservation, and like scalable and age-ready algorithm, and like beyond accuracy, we can deploy this optimized model to the edge devices as well. So those are the significance of this CAMP-HiVe algorithm, and that's it, I think. Thank you, everyone.
Okay, thank you. Okay, thanks. Okay. Now, do we have any questions?
Yeah.
Yep.
You mentioned that you use normalization methods to approximate the Hessian matrix information, and then use the merging methods to recover the accuracy stuff. So my question is, if you don't use the merging, just approximate the Hessian matrix, have you do any test on the performance of that? Just solely using the
That's what actually we did the ablation study. So in the ablation study, we did a Hessian random pairing and merging together, and the Hessian and magnitude pruning together, and magnitude pruning. So that's the ablation study is all about.
Okay.
Yeah. So you can see like our method is all of the above. So you can see it. So
So in this case, the Hessian is the approximate.
yeah, this is the approximate. Yeah.
Do we have
Yeah. Sure.
I have a question.
Yeah.
In practice, the neural network is non-convex. So the Hessian approximation may face challenges like, so is there any convergence guarantee under the assumption that the neural network is non-convex?
So if you want the guarantee,
Yeah.
so that's where the actually iteration comes in, power iteration in the Hessian approximation. So that power iteration gives us the the luxury that we don't go for the derivation of the second order. We keep it in the first order, and we keep it in the complexity in ON, not on the ON square. So that's where we can have the leverage of guarantee that it can go to the convergence to the find the region of the highest curvature of the loss function.
We have some more.
I have a very lightweight question, if you don't mind.
Yeah.
When you say latency, what does latency entail typically? All of it. So I guess you're talking about a device being super local to the drone. Is that correct? Attached or just within like one hop of a network?
Can you repeat that question again? So I just need to understand it.
So latency. So
Yeah.
you mentioned the edge computing as well, right? So I can answer that on his behalf, but he can answer first. So his question is that what is the kind of definition of latency that you are imposing here? Is it the latency is a closed loop latency or just local computing latency on the board?
Oh yeah, it's on the board latency we're talking about.
Okay.
Yeah.
So this entire work is basically avoiding the edge computing, which is one hop distance away, because that one hop distance means it's over the wireless communications, which has unpredictable delay theoretically, because you cannot predict the wireless conditions, right? So here it has a predictability because it is running on board, but we want to optimize. Essentially, we want to get a Pareto frontier in terms of latency, accuracy, and power domain.
Yeah.
So that's the main aim.
Yeah.
Yeah.
Okay. Anything additional?
I can have some critiques rather than questions as he's working, but
just one. It is not in the details. It is a question about presentation.
yeah.
You presented one new methodology. And we are waiting always when you presented the methodology, you have some goals in your case, latency, energy consumption, etc. And you are paying price. And in the entire presentation, everything, always your methodology here in this corner. There is no price. Is it possible that you develop the methodology, there is no weaknesses? That means you are not paying with anything.
Oh no,
comparing the other
there
methodology.
is weaknesses. That's where actually we said that our future research, the pairing is not optimal. The I mean the less
What is
the pairing algorithm.
a pair?
Yeah, it's not optimal. That's why we are looking for the bipartite matching and the GNN for the pairing algorithm. So this is one of our lackings in the
What
sense.
does it mean it is not optimal?
Because how to explain it?
Yes, so the thing is,
Yeah.
so he posed the pruning problem as an optimization problem.
Yeah.
But the solution, so he missed out mentioning that the solution, what he proposed, is a heuristic.
So
It's not
Yeah.
an optimized like solution, proper optimization solution. So that's why, like if you solve the proper optimization solution, the complexity will be a little bit higher. So since we are doing a fast pruning approach, we are making a heuristic approach here, which is this one.
what does it mean? Is heuristic approach connected to the application you have or configuration of the network?
Configuration of the network, more like that. But still, your question still actually is still valid. That okay, all the results we showed is that our model is still best. So we are saying that it is still suboptimal. It's not optimal. Suboptimal could be better than that, but still that conjecture will remain. That will still be better than the remaining. So my point is that. Yes, we are solving an optimization problem, and that's why once you solve the optimization problem, it is better. The other pruning approaches, they are more focused on like the training time of the pruning also, which we have not actually shown. Our focus was more inference of the pruning approach, and we are trying to make faster. We should have maybe done some comparison of pruning training, and our pruning training is not the most efficient one. We are doing some fine tuning needed. There are some one-shot pruning, a few shot pruning approaches as well, which needs lesser training time. So yes, we are not the best in terms of training or fine tuning for the pruning, but we are saying that okay, once it is pruned for the deployment purpose, our focus is to deploy the model. It may take maybe 1 month to train, or I'm saying just giving a random number. It could be 1 day, but I'm saying once training cost is not recurring cost. Training you do once, you deploy the model again and again for years for your applications. So once you want to deploy, we are focusing on more on the inference cost and not the training cost.
But wait a minute, is it influencing dynamics in the entire application? When you are talking about training, when you have changes in changes in the data, that means you are changing even in your model what will be pruning and.
In a supervised fashion, we don't. Actually, if it is a online learning or reinforcement learning kind of thing, so with the runtime data we
but
do.
If it is.
If it is a supervised case, typically we don't. Once we train the model,
you
we
don't have
yeah,
real time.
yeah. It is a real time, but we don't. Our model weights and model configuration will not change after training. Yeah.
Okay. Good. Okay. Sorry. Do we have some more questions?
I
No?
have a follow-up one. Because I noticed
Okay,
that
sure.
in your experience, some the pruning methods achieve with the better performance with less parameters of the models. So I wonder if there's any work to to do some in-depth research to examine this phenomenon. How this happen with less parameter achieve a better performance.
Which one? Sorry.
So you are saying that the accuracy is improved
Yeah, the accuracy
better than the
improved.
baseline, right?
Oh yeah.
Yeah.
So this is the common pruning, trend. You will see lots of the state of the art. The lottery ticket hypothesis. That's published in 2019. So that's a very famous paper in this field. So you'll see in that paper also. So pruning at a certain percentage, like 45, 50, or even 55, sometimes it gets better than the baseline with the subnetwork. So
if you prune very high percentage, then of course it will deteriorate the performance. But in certain lower pruning regime, sometimes you get gain in accuracy, basically.
Yeah.
So
So
will this pruning kind of degrade the capability of generalization of the model?
It might. It might. Generalization, it might, yes. Yeah.
Okay.
But that's why neural architecture search and those things are there, right? So that's why NASNet is there. So it is more focused on the application specific. That's why, yeah. All right.
Thanks. Some more? No? One more time. Thank you.